Okay, welcome to this course on optoelectronic materials and devices. This course we are going to start in now. The course will be in 4 modules, and these modules are electronic structure of materials, which is what we will start with today, about 10 lectures on this total. And then after doing electronic structure of materials, we will go on to this electrical and electronic properties of materials, about 10 lectures again, then optoelectronic device physics and basic electronic devices. I will be covering these 2 topics, these 2 modules, about 20 lectures, and Dr. Monica Katiyar will be taking care of other 2 modules, which means who am I? My name is Deepak Gupta. I am at IIT Kanpur in Department of Material Science and Engineering. Okay, so let's see the flow of these 4 modules, how this works. So essentially this course is on optoelectronic materials and devices, which means we have to tell you about optoelectronic device physics and basic electronic devices. These are the 2 things essentially we need to tell you about. In order to do so, what we need to know upfront is electronic properties of materials, hence it comes before this. And in order to understand electronic properties of materials, we need electronic structure of materials, from which we derive electronic properties of materials. So this is how this whole thing has been arranged. With this background, let us start with lecture number 1. This lecture number 1 I have written down here. In this lecture, we hope to cover, we will finish these 4 topics. One is, we will talk about conductivity of material as in macroscopic property of material. You know, we say metals are more conducting, insulators are less conducting. What does that conductivity mean? What are those numbers is what we will start with. Following that, we will start taking a view of electrical conduction in metals, how electricity is conducted in metals. And what we will do is, we will take a historical perspective. We will go back more than 100 years back, or almost 100 years back, and we will talk about Drude's theory, which really you will see is a wrong theory. That is what we are going to prove, a classical theory which is a wrong theory. Nonetheless, it is normally a starting point to understand electrical conduction in metals and start looking at why this is wrong and what else we need to do. Following Drude's theory, in context of Drude's theory, then I will talk about DC conductivity of material, and I will show you why Drude's theory became celebrated theory in its time. And finally, what I will start doing is, 4th topic we will talk about is, which I said this is a wrong theory. So, I will start talking about failures of Drude's theory. So, that is the last topic in this lecture which we will cover, and then of course, following that, what can we do to make the theory better is how this particular lecture will flow. So, let us move on with that background. Let us start looking at conductivity. So, for this lecture 1, and also subsequently few lectures, I would ask you to, in case you need more information, you could use this reference which is given in the course content itself, the Ashcroft and Mermin Solid State Physics. This is a somewhat advanced book. So, those of you who are curious could go through this also. First, I would point out to you that let us write down Ohm's law. What is Ohm's law? If I have, you are quite familiar with a term which is like this, which is the Ohm's law, which you have seen in your basic physics. The same thing we can write in form of current density, in which case I will write this whole thing as J equal to sigma E, E being the electric field, in volts per meter, let us say. This is the current density, let us say in amperes per meter square. In that case, this becomes a material quantity as opposed to resistance or inverse of resistance, which also depends on the dimension of the material. Then this Ohm's law is written in a form where dimension of a material does not matter, and then this becomes conductivity, electrical conductivity, which is in units in this case of inverse of Ohm's meter. Ohm's meter being the units of then resistivity. Anyway, if you start looking at some of these numbers, so I have written down conductivity numbers in inverse of ohms meter for several materials. Now notice, it's among the most fantastic quantities which we know of. Notice, have you seen any quantity which varies in order of magnitude from 10 to the power minus 18 to 10 to the power 8? Hardly any. It varies over a huge range, orders of magnitude, going from 8 to 18, which is 18 plus 8, about 26 orders of magnitude, which you are seeing this scale on. Among the most insulating materials we see is like quartz, with a conductivity of 10 to the power minus 18, and among the most conducting are these metals, copper, silver, even gold, somewhere around here. In between are semiconductors, which lie somewhere in between here, silicon and gallium arsenide, you see as semiconductors. But you also know that conductivity of semiconductors can be changed by doping. That means they can be increased, and hence that doped semiconductors shift towards right. So that's the semiconductor, that's the materials range of conductivity which you see in materials. Notice, this is a bulk property. In other words, it's a measured quantity. You apply electric field, you measure current density, and whatever that ratio is, you start calling that conductivity. What our job is now to understand the origin of conductivity. Where does this come from? Where does this conduction, electrical conduction, come from? What at microscopic level is happening? That's the intent of this first lectures, and Drude theory begins to try to explain all that stuff. So let's start with that. So before we do that, let's write this like this. Suppose I apply electric field E. If we apply electric field E, in that case what happens? If a mass of electron is Me, mass of electron is Me, then I could think first order as mass of electron times the velocity of this electron. This acceleration should be equal to minus, I am putting charge because it is a negative charge, and the quantity of charge is q, where I am writing q as equal to 1.6 into 10 to the power minus 19 coulombs, then q times E. I would think of this is the force. This is the force on this electron, and this force of electron is equal to mass times acceleration is what I would like to think of. Now let's look at then current density. If I look at current density, then this current density J, which is amperes per meter square, should be written as minus N Q V, where this N is number of electrons per unit volume, and Q of course is charge. So that's the current density, number of electrons per unit volume multiplied by the charge and multiplied by the velocity is the current density. What do you notice? If I want to look at conductivity, then I need a relationship between this quantity J and this quantity E, J and E. But if you notice this, if I apply electric field, which is a force, this equation tells me that velocity will increase as a function of time. So velocity will continue to increase in time. In time, if velocity increases, then the current density must also increase. That's contrary to our observation. You know that if you apply an electric field, then at an electric field you get a unique value of current density, meaning thereby if you apply a certain voltage, you get a fixed number for current. Now what this equation is saying, these two equations are saying that if you apply electric field, then velocity will increase in time. Because velocity will increase in time, therefore J will increase in time, that means current density will increase in time, that means current will continue to increase in time. That's contrary to our observation, so something is wrong. not consistent with observation. So, what is going wrong? So, let us start looking at why did this happen. What is wrong with our what is wrong? So, I will suggest that we can reconcile with our problem if we introduce some kind of damping. So, let me explain that a little further. What was our problem? Our problem was that if we applied a force which was on electron which was like this, then we said that this would become equal to mass of electron dV dt. Now, if I plot this velocity or speed, let me say, essentially the minus sign says the direction of v and e are different. This e and this v, direction of these are opposite. That is all this minus sign indicates. Otherwise, we are looking only at the magnitude. So, if I look in time and I plot this velocity or speed v, then this expression says that because you have applied this force here, hence velocity will linearly increase in time. Initially, if it was 0, initially it was 0 right here at t equal to 0, and in time it will continue to increase something like this, and that was our problem. And our problem was that then of course the current would have become minus n q v, and that would have implied that the current density would continuously increase as v increases in time. But what is our physical observation? That given electric field, given this electric field, corresponding to electric field, there is a specific current. This is what our observation, and therefore there must be a specific value, single value of this velocity which should come in this expression. What that means is that this velocity should become a constant in time. It should be something like this. So, that would happen if our velocity, instead of following this path, had followed something like this, that at t equal to 0 it is 0, then it increases, but then slowly it becomes like this and acquires a constant velocity, something like this. This should have been our nature of the velocity. If it were so, then we would have been fine. Let us call this as v sat if you wish for better choice, or let me erase this and let us call this as v sat for the moment, that we want this velocity to be saturated to some value. Now, we can do that if we include another term, which is what I was saying, like a damping term. Let us call this damping as follows. What that means is that initially at t equal to 0, when velocity was 0, then this term of course was 0, it is not contributing anything. So, whatever this total force was totally balanced by this term, and hence we had a linear increase near t equal to 0 of velocity. But as this velocity begins to increase, now this term is non-zero and it starts acquiring some greater and greater value. And therefore, since it acquires greater value and the total left hand side must remain the same, so the value of this term keeps decreasing therefore. This, which means the velocity acceleration of electron will decrease, and that is what I am showing you through this red line, that it started decreasing until it so happens that this velocity becomes the saturation velocity v sat. That means this term alone becomes equal to this term here, and in that case this whole term should go down to 0. This whole term should go down to 0, which means dV dt should go to 0, and then we have the saturation portion, and we will acquire that. And hence it will be better if we include, that means what our physical observation is, that there must be some sort of damping term also coming in, which we haven't included. Now, notice that if we had this damping term, then when we have reached the saturation velocity, and in some time this time interval we have reached the saturation velocity, but after that then it should have become, this expression should have become minus q E equal to gamma v sat, because in this case dV dt will be in this region, dV dt will be 0, and that means I have value of E implies that E is equal to or rather I should say let me do V. So, V saturation, so this V saturation what we are writing as should be equal to minus q E by what is there, gamma, this factor, this damping factor which I have included, which means if I substitute back into this expression, then J would become equal to n q, another q coming from q square. I am substituting this V into this, because this is the saturation velocity when this current corresponds to this velocity. This velocity is corresponding to which I have calculated this current density. So then I am substituting this V sat in this V here to see what happens. So Q NQ square E divided by, I would get a gamma in there. So that's right, yeah. So this, now notice, you will see this is now for a E field, I get, if I apply a field E, then I get a current density called J. I get a current density equal to J, and they are related through this term. So essentially now you can see that if I had some sort of damping, if I had a damping factor in here, then I would have gotten my physical observation, I would have matched my physical observation. So essentially now next question would be, what is this damping factor? What is this gamma, or where does it originate from? Does it originate from? So this is the question. We therefore, if we answer this, then at microscopic level we will be able to tell you what is the origin of this conductivity in a material. Could it be let us say lattice atoms with which electrons collide, or impurities, or grain boundaries, or anything that gives imperfection in a lattice. So essentially I am hinting towards where we are heading. Essentially what I need is damping. That damping must come from somewhere. An electron going around could collide with atoms, could collide with impurities, grain boundaries, anything which breaks the, anything which can break the periodicity of lattice could therefore cause scattering. And so therefore essentially understanding gamma means understanding these processes. With this, then now let us move on to what is a classical view of conduction. So with this we will move on to classical view of conduction. Now imagine this, imagine at turn of 20th century in 1897, J. Thomson had discovered electron already, electron was already known. Second thing, what we maybe electron also we knew at this point of time was kinetic theory of gases. That is what we want to do, Drude's theory. So Drude was aware of electron, was aware of kinetic theory of gases, but what was known at that point of time was structure of atom. Structure of atom was not known. So this is what is beautiful about this theory, that Drude, who did not know the structure of atom at the time, went on to make assumptions about the structure of a material, and he proposed he made certain assumptions. Based on that explained the conduction in metal. So we are going to go through that. Before doing that, let me start here again. Drude's theory, what we want to do, based on of electron this was not known at the time. So, Drude went on to hypothesize what is going on. He assumed, Drude assumed electrons which are charged carriers conduct. City in metals. Since, now this is an important statement he makes, that since there is an electron, a negative charge, then there must be a compensating charge. So, he makes assumption a compensating charge in form of ion which is positively charged. Positively charged. He makes assumption that there is a compensating charge which is an ion which is positively charged. Now, remember, this is in the time when there is no structure of atom is not known. He is making this assumption because he needs to put a compensating charge. Another thing which he does is that he says ions are heavy, hence immobile. This is another assumption he makes. This assumption you see in connection with the first one, this assumption that electrons conduct electricity in metals. If we had that is connected, that in the sense that ions do not conduct, there is electrons and then there is a compensating charge. That compensating charge is a positive charge and this is being called as ions, and then it says that since electrons conduct, which means ions are not conducting, that means that ions are immobile. Had they been moving, then they would have also been conducting. Therefore, these are the basic things he assumed, and beyond that what he did was with these assumptions, with these assumptions, Drude applied kinetic theory of gases to electrons in a metal. Now, remember, kinetic theory of gases really is valid for dilute gases. That means, distances between gaseous atoms is large. Now, electrons, can we think of them as electron? Can we think of that as a gas, or they are too close to each other? That we need to see. So, let us see how many electrons are there that are conducting. So, let us look at this. Suppose Z electrons from one atom of metal conduct. What does that mean? If we think that there is a valence, there are valence electrons, the tightly bound electron, and that the outermost shell, whatever the number of electrons are, those are conducting per atom. That means, for lithium, for example, there is only one electron in the outer shell, rest is the part of ion. So, you think like this, all this nucleus and all these inner shells of electrons, these are the ion. This is the ion and this is the valence electron. Valence electrons which are around, which are valence electrons, these are the ones which are conducting, and this is number is Z, suppose in this case shown as 3. So, these are the electrons which are conducting. So, if these are the electrons which are conducting, suppose that we have rho m is the density of metal, that say kg per meter cube. This is the number of this is the density of metal. If we divide it by the molecular weight of the metal, if we divide the molecular weight of metal, then I have things in moles per meter cube, moles per unit volume, this many moles. If you multiply that by Avogadro number, multiply this by 6.023 into 10 to power 23, then I have this many number of atoms per unit volume in a metal. And if I multiply this by Z, which is the number of electrons per atom which are conducting, then I have number of electrons per unit volume per meter cube of electrons which are conducting, and that number is n therefore. So, n is number of electrons, number of conduction electrons per unit volume in a metal, and these of course rho m is density and m is molecular weight. So, m is molecular weight. So, this is the number of electrons that are going to conduct in case of Drude theory. These numbers you can plug in value. I will show one case eventually. So, n typically will vary between 10 to power 22 to 10 to power 23 per centimeter cube. In per centimeter cube of metal, therefore, this is number of electrons that are there for conduction. So, if this is the number of electrons, then what did Drude do? After this, of course, now given this per centimeter cube, this many is number of electrons, then you can, what you can do is take inverse of n, 1 over n. That means per electron volume associated with per electron you can calculate, and from that you can get an estimate of what is the distance between electrons. You would find, of course, that these the electron gas is really dense. And remember, kinetic theory gases can be applied only to dilute gases, but nonetheless Drude went ahead and applied this to electron gas in metals. Electron gas he went ahead and applied this theory to electron gas in metals, though now given that the 10 to the power 22 to 10 to the power 23 electrons per centimeter cube, it is really dense, and still he went ahead and applied kinetic theory of gases. So, assumptions are similar to kinetic theory of gases, and those are like this. The electrons are both. So, let us start looking at the assumptions of Drude theory. He makes the assumptions that the electrons are both independent and free. What does that mean? He says that these electrons which you have, an electron is an independent electron. Assumption implies that between two collisions. So, he is assuming what he did was, so what he assumed is that these electrons are moving around in a metal, then they collide with ion cores, these ion cores which are immobile, compensating positive charge, and then they move away, and this is his picture of how electrons are conducting. So, this collision and then evolving of electron out of this collision provides really the damping, that gamma factor in Drude theory, so that the velocity does not continuously increase. What it does is that an independent electron assumption implies that between two collisions, that means electron comes and collides one ion, emerges out of it, and then collides another ion. Between these two collisions, an electron does not interact with another electron. Independent electron means that there is no electron-electron interaction is what it means. Therefore, in absence of an applied field, an electron moves in a straight line, and in presence of a field, electron trajectory decided by the field. But in both cases, the field due to other electron plays no role. So, understand this, that electron comes out of this collision and it is going to collide again with another ion. Since it does not see other electron, it does not interact with other electron, it does not see other electrons field. So, therefore, it just continues to move in a straight line. If you apply another external field, then of course, it follows the external field, but not if you do not apply the external field. Similarly, you think of free electrons. So, there is an independent electron I have just explained. Similarly, you can think of free electron approximation, where he also neglected, remember this electron and ion would have a Coulombic interaction between them. but he says that these are the valence electrons which are very loosely bound. That means whatever the positive charge is, whatever the charge is, it's shielded by so many inner shell electrons. So the inner shell electron screen the positive charge in the nucleus, and therefore this electron is very weakly interacting with them. He makes assumption that this interaction is nearly zero. That means between the electron and ion interaction is ignored. Thus, the field produced by both electron and ions is also neglected, and that is called free electron approximation. So, that is the two major approximation he makes, independent and free electron approximation. Then these Drude's electrons, the Drude's electrons which he has, about which he has made this assumption of independent and free, they collide with ion cores, and when they collide, what happens? The moment they collide, here is the ion core, this is the electron, this comes and collides with it, and then what happens? Then they change it comes out with some speed, it changes its speed and the direction, this electron, and of course, this ion core is immobile, this is sitting heavy and it is sitting there. So, therefore, scattering is happening because of the ion core. That means, electron comes, hits it, and then it changes direction and speed. So, that is what happens in case of Drude's model, but electron scattering is neglected. That means, an electron does not interact with another electron and gets scattered. It does not change the direction of speed. Since we are not assuming any electron interaction, so that it is not possible for another electron does not change the direction or the speed of this electron which is going by. So, that is his second assumption which he makes out of the total 4 assumptions which are inherent in which are Drude's assumptions. So, these are the 2 major assumptions. Then let us look at the third assumption. Now, he says that there is an ion here, there is an ion here, this electron collided with this and then evolved in this direction and started in this way towards this direction. Probability that an electron experiences a collision per unit time is 1 by tau, which means if you think that average time taken between collision, on average whatever the time spent is tau between collisions, then you can think of probability of an electron experiencing a collision in a unit time is then 1 over tau. That is what he is assuming here. So, this tau is known as the relaxation time or mean free time, time between on average this is the time electron. So, on average if you pick an electron picked randomly will experience next collision after time tau. So, that is the time on average the time which is spent between collisions by electron. So, that is the definition of relaxation time in Drude's model. And finally, the very important one. Now, I have an ion and an electron comes and collides with it. It is coming in this direction and it has a certain speed. Question is, when it is scattered, which direction will it go? Second, what will be its speed? Third, will it have a history? Will this speed be dependent on what the speed earlier was? So, this is the third assumption Drude makes, that electrons reach thermal equilibrium by collisions. That means, when it comes and hits it, then it reaches, then it thermalizes, thermal equilibrium is attained by this process itself. What does that mean? That means that the velocity of an electron just after collision, that immediately after the collision, is dependent only on the surrounding temperature. It depends on the surrounding temperature, and therefore, it evolves in a random direction. It could go in any random direction. It does not matter electron was coming from here or electron was coming from like this or electron was coming like this. The incoming electron came like this or like this. It does not matter from what direction it came and collided. It evolves in a direction which is random, and its speed is entirely dependent on what the local temperature is, because that is how it reaches the thermal equilibrium, which means that after collision the evolution of speed is based on thermal equilibrium in random directions. It has no history, that electron does not remember what speed and what direction it came from. These are the 4 major assumptions. Based on this, therefore, the Drude theory evolves. So, these are 4. This is essentially the Drude theory. Now, we are going to apply this Drude theory and start looking at DC conductivity in metals and see what it means to us. That is what we are going to do now next. What do I mean? Question is, when you apply an electric field, what happens? Absence of an electric field, what happens? The average velocity of electrons is 0. It is exactly 0. Why? Remember, electrons collide and then they emerge out of this collision in random directions, in random directions, and velocities which correspond to the local temperature. If you think of Maxwell-Boltzmann distribution, then also they with a random set of velocities also. Therefore, in random velocities in random directions, net effect is that in absence of an electric field, the average velocity of electrons is 0. What happens in presence of electric field? In presence, an external electric field what happens? Now, you see between collisions this electric field E will start having impact. Suppose an electron emerges out of collision by velocity v0. Let us say this is the velocity. That means, here is the ion, electron collided with it. When it came out with this velocity v naught, and this v naught is a random velocity, random direction, random speed, not determined by any external field. But now, once it emerges out of this v0 field, then after this what happens? How this velocity evolves of this electron depends on what the electric field is. So, according to the what the field is. Therefore, in time t, this velocity after a collision, being this v0 velocity, after a collision, the velocity changes in time t. The velocity changes from v0, changes by an amount which is equal to what? This change is equal to, if I think of minus q and E as the force divided by mass of electron is the acceleration, into time t, this is the quantity by which changes by this quantity. Then by this quantity, then the velocity changes. Since average of this t, the time between collisions, the time it emerges out of one collision, and then let us say in t time it increases, the velocity changes by this amount which is written out here, and then it collides with the next electron, the next ion. The electron collides with the next ion. So, this is the change of velocity during that time. So, on average, since this time, average of this time t is tau, tau is the average time between collisions. Therefore, V average is equal to minus q E m e tau. Remember, v0 is a random velocity. v0 is a random velocity from which this is the ion, and here is the electron which came out with velocity v0. So, this is the velocity by which came out, and this is a random velocity. So, therefore, average for, and it came out in random direction. So, average of this velocity is of course 0. So, only part in presence of electric field, only average only contribution to average field to average velocity due to electric field is therefore this. This is the change in average velocity due to electric field. Once I have this, now you see, now this V average depends on electric field. Given electric field, there is an average component velocity, that's now no more, does not increase in time, because this is the average time in there, this is a fixed number. So, no more, now I have a fixed velocity in here, in which what that means, now current density is equal to minus n q V average, as we wrote earlier, which now I can write as equal to, implies that J I can substitute now in this case this velocity, therefore, we can write n q square E by tau by m of E, implies that conductivity now is n q square tau by m E. So, now we have derived in Drude's theory, according to Drude's theory, what the conductivity of a material therefore will be. Okay. So, now what we have done, now this is a consequence of Drude's theory, based on the assumptions we made about this relaxation time, what definition of relaxation time. Now, what happened was that because electron comes and hits and forgets about its past and emerges out of it by according to the whatever the velocity is according to thermal equilibrium, what that means is that average of that velocity is 0, and that essentially means damping. Again and again the electron is getting damped. But if I apply electric field, then only contribution which comes is due to electric field, and since tau is the time between average time between two collision, there is correspondingly there is an average velocity which electron gains between two collisions, or this is the average velocity of all the electrons. Now, if I have average velocity, so I have a current accordingly. Once I have a current, then I have once the current and proportionality between J and electric field gives me the conductivity. Hence, I have a conductivity of the material. Now, what have we gained? Let us start looking at sigma. We wrote as n q square tau by m E. What have we gained? Essentially, what has happened is, now earlier we had a measured quantity called sigma, which was relationship between proportionality constant between J and E. The proportionality constant between J and E, it was a measured macroscopic quantity. Now, we have gone one level down and established a mechanism by which this conduction happens, and accordingly obtained this relationship. So, in that sense now, but then I know what n is, I know what q is, I know what mass of electron is, but again I am stuck with this quantity tau, which I do not know. Essentially, I still have not figured out what the conductivity of material is. I have merely changed my problem from knowing sigma to knowing tau, which is the relaxation time. But now, instead of macroscopic level, we are talking about at microscopic level. So, that is what we have gained. We have gained a microscopic picture, but my problem in knowing what the conductivity still remains where it is, because I still will have to measure tau. I have no means of knowing what tau just yet is, at least. So, what does that mean? Let us just start looking at, so is this theory good or not? So, let us just first start looking at this quantity. Now, let us look at this. Let us make an estimate what value of tau is. Let me put down some numbers. Let us say copper. Its molecular weight is equal to 63.5 grams. So, I am going to put this as minus 3 kg. Its density of copper is equal to 8.96 grams per centimeter cube, or 10 to power 3 kg per meter cube, Now, therefore, and its conductivity we know is equal to 5.8 into 10 to power 7 ohms meter inverse. That is what its conductivity is. So, now let us estimate what, assuming Z is equal to 1. Let us assume Z in copper is equal to 1. That means 1 electron per copper atom is conducting. This you could argue that no, it is not 1, it is it's d and s shell electrons, meaning 11 electrons, but we will see that also. But for time being, let us assume that is only s shell electron, 1 s electron which is conducting in copper. In that case, we calculate now based on the formula we had derived, and calculated is equal to in fact, you can calculate this 1 into the density is 8.96 into 10 to power 3. This many kg per meter cube divided by molecular weight is 63.5 into 10 to power minus 3 moles per meter cube into 6.023 into 10 to power 23 number of atoms per meter cube, and since there is 1 electron per atom, so this many electrons, which is equal to, I have calculated as 8.49 into 10 to power 28 electrons per meter cube, or 10 to power 22 electrons per centimeter cube, and mass of electron is 9.11 into 10 to power 31 kg, charge of electron 1.6 into 10 to power minus 90 coulombs. Therefore, based on that, if we plug in all these numbers, into our formula right here, then what do we get tau as? Implies tau is equal to, all these numbers include sigma also in their conductivity. So, tau is calculated as 2.43 into 10 to power minus 14 seconds. That is what the value of tau is. So, depend if you had chosen therefore Z as equal Z an order of magnitude higher, in that case your, so let us say tau therefore will say varies between 10 to power minus 14 to 10 to power minus 15 seconds is tau. Now, if you look at the velocities involved in these materials, if we think since Drude this kinetic theory of gases being applied, there is thermal equilibrium being assumed, then it is reasonable to assume also from the ideas inherent in kinetic theory of gases that velocity could be estimated as half mv square as equal to 3/2 by equipartition of energy as Boltzmann constant times temperature, that local temperature. So, this at room temperature, this velocity is approximately equal to 10 to power 7 centimeters per second. That is what the velocity is. So, therefore, if you look at mean distance between collisions, then this will be the velocities which are involved, order of magnitude of velocities. Of course, this is the velocity by which electron will emerge out of collision, whose average component is 0, but that is the order of magnitude of velocity, and multiplied by tau, that the average time between collisions, then this distance therefore will become equal to about 1 to 10 angstroms based on value of tau and V0. So, now this became the proof of Drude theory, that this is good theory, because interatomic distances are on that order 1 to 10 angstrom, and since he assumed that the conductivity is arising out of electron colliding with these ions, therefore, and since this theory now starts predicting L which is equal to on same order as 1 to 10 angstroms mean distance between collisions, therefore, then and it is matching the interatomic distance, then it appears therefore that this is a good theory. So, now let us start. So, this is why this basic idea of Drude theory, but what I will start telling you about is now failure of Drude's theory. From modern, we will see from modern quantum mechanics. Remember, electron is a fermion, which means it follows Fermi direct statistics. And so, if I take as quantum mechanical theories, then velocities are an order of magnitude too low. in what we have taken in the classical theory, and tau is in fact, whereas tau is an order of magnitude higher in what we have so far taken from reality. The two errors cancelled out and L turned out to be pretty decent. That is where the, while it appears that the Drude theory is good, but there is a problem. Second thing is, it does not say anything about, for example, in copper, if you make a take a really pure copper and go down to very low temperatures, then this mean free path, mean distance between collisions may be as high as an order of centimeters. So, here is another problem which you will see. But let us look at some more points which I will not derive, but I will merely point out to you where the Drude theory begins to fail. For example, take Hall coefficient. In the context of in the context of Drude theory, if I look at the Hall measurement, Hall coefficient, with which I will assume that you guys are familiar. If you are not, maybe read up a textbook on Hall effect, which is taught to you in school also. But assume that this, you know this, there is a Hall coefficient which is equal to, which is derived as minus 1 over n times q. Notice now this, remember when we started looking at the mean distance between collision, there was v velocity term, there was tau term, and these two the errors cancelled out and the Drude theory appeared okay. So, what we are doing right now, we are trying to apply the Drude theory to essentially those places where only one property occurs. That means, in this case here it is, we have it is independent of tau. So, now let us see what happens to Hall coefficient. What we find is n we can calculate, what we find is for lithium, sodium, potassium, cesium, good agreement with measurements. That means, you calculate RH based on n, we can calculate, I have shown you calculation for n, you calculate n for lithium, sodium, potassium, cesium, etc. Substitute in there, calculate what RH is, also measure RH, and if you measure RH through Hall measurement, of course, then you will find that there is a very good observation between theory and measurement, which says that Drude theory works. But then it works okay for noble metals like silver, gold. It works okay. Does not work, not good for beryllium, indium, magnesium, indium, aluminum, where RH is positive. It turns out that RH changes sign, the sign itself is wrong, meaning thereby that it appears, if you do a measurement. So, if you take say aluminum and you think 3 electrons are conducting and you calculate RH with aluminum here, and if you, and it will be of course a negative value, and if you measure it, then you find that RH is a positive quantity. It will appear therefore in aluminum, in measurement it will appear as if it is not electron conducting, but it is like a positive charge which is conducting, and it turns out if you do it properly, you will find that it appears as if one positive charge is conducting rather than 3 negative charges conducting. So, what is going wrong? Drude theory cannot explain this. So, that is one failure which I would like to point your attention to. Similarly, if you look the magnetoresistance, that means resistance in presence of magnetic field. If you look at magnetoresistance, then this quantity is ME divided by N Q square. For this part, either you can read the reference, if you are really interested, you can read the reference which I have given you in Ashcroft and Mermin, or you can just follow this text, assume in Ashcroft and Mermin all these quantities derived. So, those are something which you can take a look at if you are interested in where these formulas are coming from, but in context of this class, it's not. What I am going to do is just give you these formulas. What I am trying to point out here is, now this is a quantity which is tau dependent. It is tau dependent. If there is an error in tau, then this rho mr will, if there is an error in tau, how we estimate tau from conductivity measurements, then independently, if you try to match with rho mr, you should be able to see if the Drude theory is right, they should match. If the Drude theory is not right, they will not match. What you find is that this quantity is field independent. Independent of the magnetic field that you apply, but in practice it is not so. If you take a measurement, then it turns out to be field dependent, and if according to Drude theory derive this, you calculate, then it becomes independent of field. Similarly, I will take you one more, a plasma frequency. A plasma frequency is a quantity derived as n q square divided by me into dielectric constant or permittivity of material. What is this? This is the plasma frequency. For if you take for electromagnetic radiation, of omega greater than omega p, this metal is transparent. For omega less than omega p, metal is opaque, meaning that if you have electromagnetic radiation, I have metal electromagnetic radiation, there is something defined quantity called plasma frequency. This electromagnetic radiation will get absorbed in this metal, and it won't go through if the frequency is less than this plasma frequency. If this frequency of this electromagnetic radiation was greater than this quantity plasma frequency, then this electromagnetic radiation will go through. That means the metal will look transparent to that frequency. That also can be now seen in context of Drude theory, and what we find is that for lithium it works very well. For lithium, we find that lambda plasma frequency, the wavelength of plasma frequency corresponding to this is equal to, I have a number for it, theoretically it is 1.5 into 10 to power 3 angstroms, and lambda p measured is equal to 2 into 10 to power 3 angstrom, pretty decent match in terms of plasma frequency for lithium. But for most other metals, maybe use the next page, for most metals, this match is not good between theory and observation measurements. So, these are few examples of failures of Drude theory. At this point of time, I will stop, and in next lecture I will try to show that where these errors may be, where the problem may come from, and then start developing a theory which is much better than Drude theory, and it is a more modern theory based on quantum mechanics, as you will see. Thank you.